Hello, I would like to welcome you to this video on some diode examples. I will try to explain different regions of operations of the diode and then illustrate it through three examples. The most important thing to remember here is that the diode can be in one of three regions: forward biased, reverse biased, or the breakdown region. And as we did before in all examples or active devices, you have to assume a region of operation and then verify it. So let's take a look first at the theory and then we'll move to discuss the examples. We studied before for a couple of courses so far resistors. We know what is the IV characteristic of a resistor. This is a resistor here. So you apply a voltage V between this terminal and this terminal, you get a current I flowing in the resistor. If the voltage is zero, the current will be zero. When the voltage increases in the positive direction, the current will increase in the positive direction. If you reverse the polarity of the voltage, current will start to flow in the opposite direction. So this is a relationship between the voltage and the current. It's a linear relationship. It goes through the origin, because when the voltage is zero, the current is zero. So the diode can be looked at as a nonlinear resistor. It's still, the characteristics still go through the origin, but it really, of course, it's an active device, so the current can be significant, but it's not linear one. It's actually given in the forward direction by an exponential curve, and then in the reverse direction, when it reaches breakdown, it also follows some sort of an exponential curve as well. So this is a characteristic of the diode. So you can see this is let me go back here. So this is the diode here first. So we have a voltage, a VD, applied between the anode and the cathode. We call this terminal the anode, this terminal the cathode. So when this is positive, okay, this is positive, then you have a current. A current will flow here only if this voltage almost reaches 0.7. Below 0.7 is not passing much current. Okay. So unlike the resistor will pass current even if VD is small, positive but small. The diode will not pass current unless the voltage, the V diode, is at least is around 0.7. Let's put it that way. If you reverse the polarity, then there will be no current flowing unless the voltage between the cathode and the cathode becomes significantly higher than the anode by V zener, and this V zener is one of the characteristics of the diode. So in that case, if this is the case, you have a voltage difference of V zener between the cathode and the anode, and the current start to flow in the opposite direction. Okay, so remember, the current in the diode can be in the forward direction if it is in the forward region. It can be in the reverse direction if it is in the breakdown region. And this is the complete characteristics of the diode. This is here when you increase the voltage from 0 to around 0.7, the current is small here, and then suddenly it sees an exponential growth around 0.7. So we usually ignore this transition. It's a little bit sharp transition, and we try to approximate it by this vertical line. The same thing will happen for the voltage. If you make the anode voltage relative to the cathode to be negative, then you can see that there will be no current flowing until the cathode becomes significantly positive than the anode, and in that case you end up getting current flowing. So once you reach, say, if V zener was equal to 9, so once the anode to cathode voltage becomes -9, which means that the cathode is higher in voltage by over the anode by 9 volts, then current will start to flow. The value of the current is really determined by the circuit. So if the diode is forward biased, the current can be 1 milliampere, it can be 2 milliamperes, so it can be at this point, or it can be at this point. It depends on the surrounding circuit. The same thing in the reverse region, in the breakdown region. The current can be here, so it's minus 1 milliampere, so 1 milliampere flowing from the cathode to the anode, 2 milliampere flowing from the cathode to the anode, 3 milliampere, and so on, depending on the surrounding circuit. The resistors and so on are what limit this current. Okay, so we usually don't use the exact characteristics. It's a bit nonlinear curve. It requires solving a nonlinear equation using a technique like Newton-Raphson. We approximate it using this one here. We call this voltage the forward voltage, VF, and this one here is called the zener voltage. Zener voltage is usually given as a positive number. Say the zener voltage is 9 volts. So this means that when the cathode is more positive than the anode by 9 volts, then the diode will enter the breakdown region. Okay, let's take a look at this example. We have a network of resistors and we have this diode. We'd like to determine the state of the diode. Is it on or off for breakdown? Okay, in the breakdown region. And we'd like to determine the current and voltage everywhere in this circuit. Okay, how things go. So you could see we have to make an assumption. Is it in the forward region, breakdown region, or is it off? Now, because of the polarity of the battery, this battery is trying to push current in this direction. So if the diode is on, current will flow in this way, flow in this direction. So it will flow from the anode to the cathode. So this diode has to be either off or it is in the forward region. It cannot be in the breakdown region because of the polarity of the battery. For the breakdown region, the current has to be flowing in this way, from the cathode to the anode. So this is not the case here. This circuit does not allow such a condition. Then this diode is either off, so this means it's open circuit, there is no current here, so this I diode will be 0, or it is on, and then the voltage across it is 0.7, and this diode current will have some value, and this value will be determined by the circuit. Okay, so first we make the assumption that it is off. I made this assumption my solution. If it is off, this means there is no current here. So this resistor is really hanging in the air, so there is no current flowing here. If there is no current flowing here, means that the voltage here is the same as the voltage here. So V diode, the voltage between the diode and ground, between the anode of the diode and ground, between the anode of the diode and its cathode, is simply equal to the same voltage as this one here. But what is this voltage? This voltage now is a voltage divider between 4.7K and 2.5K. Okay? So we have to determine this value and see whether it is sufficient to turn the diode on or not. Okay, so here is the circuit. I first assume that the diode current is 0, so there is no current flowing here. And if this is the case, then this is hanging in the air. This is not part of our circuit because there is no current here. But this means that the diode voltage, this voltage here, is equal to the voltage V1 because there is no drop across the 4.7K. Now what is V1? V1 is a voltage divider between 4.7K and 2.5K. So it's equal to 30 multiplied by 4.7K divided by 4.7 plus 2.5K. So if you calculate this one, you get 19.58 volts. So now we reach the contradiction. Why? Because I assumed that the diode voltage is less than 0.7. But through my solution, I found that the diode voltage is equal to V1, and V1 is equal to almost 20 volts. So the diode has to be on. The diode is not off. Okay? So once the diode is on, this means that it represents between the anode and the cathode a drop of 0.7. So here between this terminal and this terminal, you have a drop of 0.7. So you can replace it in your calculations by a battery of value 0.7 and try to determine the current that's being synced into that battery. This battery will not supply current. It will actually sink current. So the current in this battery, as you see, will be flowing in this direction. Will be flowing from the anode to the cathode. So let's see how we can analyze this circuit using the techniques that we learned before in circuit analysis. So now we assume that the diode is on. So I have a current. There will be a current flowing everywhere in the circuit. A current I1 here, a current I2 here, a current ID here. Okay. Then this is a typical circuit with two loops and with one node. So we can apply nodal analysis. Nodal analysis is the easiest way of solving this circuit. And you can simply say that 30 volts minus V1 divided by 2.5K, which will give me the current I1, is equal to the two currents flowing out. This current I2 is V1 divided by 4.7K, and this current ID is equal to V1 minus 0.7 divided by 4.7K. And this is what we have here. I removed the K. I removed 2.5K here, K here, K here, because it doesn't matter. This is simply 1,000, and I have two sides. I can simply delete them. Okay. So if you multiply 4.7 both sides by 4.7, you get 4.7 divided by 2.5, it's 1.88. And if you simplify, you end up by V1 equal to 14.716. Okay, so what is the current I1? Can I get I1? Yes, I1 is simply equal to 30 minus this voltage 14.716 divided by 2.5K. What is the current I2? I2 is equal to V1 divided by 4.7K. So it's equal to 14.716 divided by 4.7K, 3.131 milliampere. Can I get the current ID? Yes, ID is simply the difference between I1 and I2. So if you subtract this one from this one, you end up by ID equal 2.982 milliampere. So the voltage across the diode is 2.98, is 0.7 volts, but the current through it's 2.982 milliampere. What determined that current? It is simply the surrounding circuit. Okay, so this diode indeed has to be on, and it has this current here. It's sinking this current 2.982. So this current is flowing from the anode to the cathode, and the diode is in the forward direction. So if I wanted to plot the point of operation of this diode, it is actually here somewhere. Okay, it is here. This is 0.7, and this one here is 2.982 milliampere. Okay, so this is my point of operation, or called the operating point of this diode. Okay, one other interesting application for diodes is in waveforming. How to create new waveforms from a sinusoidal signal or from a square signal, depending on the input. So here we have a circuit. It's a waveforming circuit. You have an input. This input is applied at between these two terminals, between here and here. Okay, and it has this profile. It has an amplitude of 10 volts. So it has 20 volts peak to peak. Okay, and I have two diodes, D1 and D2. Both of them have, of course, it's not mentioned. You take automatically the forward voltage to be 0.7 volts. And if the zener voltage is not mentioned, this means it is very high. Then the diode cannot enter the breakdown region. Okay, so it's very important to understand this. If I don't give you the forward voltage, you take it automatically as at 0.7. If I don't mention the zener voltage, then it's automatically assumed it's too high, and the diode is not likely to enter the breakdown region for this circuit, given the voltage, the applied voltage. So we'd like to determine the output waveform V output of T correspond to this input waveform. Okay, we have now two branches in parallel, so we have to see what is going to happen for each branch. We have this diode D1. For this D1 to conduct, if it conducts, then the voltage between this point and the ground must be at least must actually reach 5.7. So if the input voltage is below 5.7, you will get nothing here. Okay. The same thing is happening for the other diode. For this diode, to allow current to go in the forward direction, so from the anode to the cathode, current will be flowing this way, the voltage between this point and this point will have to be equal to 5.7. Otherwise, there will be no voltage. But this is a negative voltage. So if the input voltage exceeds 5.7, this branch will conduct. If the input voltage drops below minus 5.7, this branch will conduct. Okay, so of course what you can do, you can apply, you can follow this waveform voltage by value by value. So at time t equal to 0, you say, okay, I have 0 volts. If I have 0 volts here, can D1 be on? You'd say no, D1 cannot be on, because this battery is trying to push current in the reverse direction. Can this diode be on? No, this diode cannot be on, because this battery is trying to push current this direction, again in the opposite direction relative to this one. Okay, so someone may ask, okay, maybe this battery can push current along this one. Well, you have 5 minus 5, you get 0. So there isn't 5.7 here. Okay, so you are still waiting for your input. Okay, so you start to apply your input signal. You make it 2 volts. If you make it, say, 2 volts, is this sufficient to turn this one on? No, because you need 5.7. Okay, if you have 2 volts here, with this polarity, say this polarity here, okay, is this sufficient to turn this one on? No. Why? Because this is added to this reverse voltage. This is negative positive, this is negative positive. So the reverse voltage applied this one even becomes 7 volts. So this one doesn't turn on, okay? So when the voltage reach 5.7, this is when this one will conduct. What is happening before the input voltage reaches 5.7? Both branches are off, okay? And you have the input voltage being transferred to the output. So V output will follow V input for all for all positive input values up to 5.7. But when you reach 5.7, then the first branch will conduct. Okay, so this is done at 5.7. Okay, so you have 0.7 here, and you have 5 volt apply along that battery. So in that case, current will start to flow. So once the voltage exceeds 5.7, there will be some current flowing here. The remaining drop, say up to, when you have an input of 10 volts, 5.7 will appear across this resistor and the battery. Sorry, across this diode and the battery, and the remaining voltage will appear across this 1K. So there will be enough current flowing this way, okay, to allow the circuit to satisfy Kirchhoff voltage law. So this input voltage, V input voltage, will be equal to this drop plus these two drops as well. Okay. Now what will happen for a negative supply or negative input voltage? If you apply a negative input voltage, again, you need at least to make this point higher than this one by 5.7. So below that, or higher for higher values, the output will still follow the input. But when you reach that point, again, the diode will conduct, okay, and you end up, the output is fixed at minus 5.7 volts as long as the input drops below 5.7. Okay, where does the rest of the voltage go? This is minus 10, say. If you have here minus 10 between this point and this point, where does the rest of the drop will go? It will go across this resistance here. Okay, this resistance will absorb, so the remaining current, remaining drop, and the current in this case actually is flowing this way. Okay, because it's a negative supply voltage. Okay, so if you apply positive, negative, the current will start to flow in this direction. Okay, so in the forward direction, current flowing this way. In the reverse direction, current flowing this way. But for this one to flow, the input voltage must exceed 5.7. For this one to flow, the input voltage must drop below minus 5.7. Okay, so as I said, D1 will conduct, the first diode will conduct if the input exceeds 5.7. D2 will conduct if the input voltage drops below minus 5.7. And when they reach that value, the output voltage is clipped, is trimmed at 5.7, because if you remember the circuit, you have a diode and then you have a battery. Okay, so once the diode conducts, the voltage between these 2 points is equal to 5 plus 0.7. Okay, so once it conducts, it clips the output, and the output remains fixed 5.7 until the input drops below 5.7 again. And the same thing happens for the negative cycle. So this is the output waveform. So the input waveform is still sinusoidal, going minus 10 to 10, and the output waveform is one that goes from 0 to 5.7. It remains trimmed, and then it follows sine again up to minus 4.7, and then it gets trimmed, and so on. So this is a typical application for diodes to use them in doing waveform. So this circuit, by the way, or this waveform approximates more a square wave. So we can pass it through a filter and then get a better defined square wave. Okay, we have one more example here. We have 2 Zener diodes connected back to back, and we'd like to determine the output waveform, given that we have this input waveform from minus 10 to 10. And for these 2 Zeners are not identical. This one here has a breakdown voltage of 3.3 volts. This one here has a breakdown of 5.1 volts, but both of them have forward voltage of 0.7 volts. A Zener diode is nothing but a diode. Okay, so if I put a symbol like this one, this is simply exactly a diode. So it will exactly equivalent to a diode pointing this way. If this is a Zener, okay, so it's exactly equivalent to a diode pointing this way. But a Zener diode is the doping levels in the diode are selected such that it can reach breakdown earlier. Okay, but it still allows current to go in the forward direction, so current can flow here in the forward direction, and it can allow current to go in the breakdown region once the breakdown voltage is reached, once the zener voltage is reached. Okay, so you have to pay attention to that. So in this circuit, we have this circuit here. So you have two zeners, Z1 and Z2. How can a current flow in this branch? How can I get in current this branch? Well, the branch containing the zener 1, Z1, and Z2. Well, there are two possibilities. This one can be forward bias, so this is a diode. It will allow current to go in this way, and this one is in breakdown region. Okay, but for this to happen, you must have a voltage drop here, okay, and a voltage drop here. The voltage drop, this is forward bias, so this one will be 0.7. This one is a breakdown region, this one will be, as we said, 5.1. Okay, so if the input voltage exceeds 5.7 plus 5.1, which is 5.8, then a current will start to flow in this direction. Okay, so you can see here we have a case where two active devices connected together, and they can both conduct simultaneously only if they are in two different regions. One of them, which is this one, will be in the forward region, so it will have a drop of 0.7 between the anode and the cathode. This one will be in the breakdown region, so the voltage between the cathode and the anode will be 5.1. So for us to be able to enter that region, the input voltage must be at least 5.8. Because if you have an input voltage below that, you don't have enough voltage to make them enter this region, and in that case, you have V output is equal to Vn, and this is open circuit. Okay? So I'm now talking about the positive side of the cycle. So if you apply 0 volts, well, 0 volts is not sufficient to turn anything on. The output is equal to the input. If you apply 2 volts, say the input voltage is 2 volts. So you have 2 volts between here and here. Okay? Well, 2 volts are not sufficient to give this 1.7 and give this one 5.1. Then this branch is off. And then you still get 2 volts at the output. So the output will follow the input until Vn will reach 5.8. Once you reach 5.8, so at this point here, say, once you reach 5.8, okay, then in this case, your assumption that both are off is not true, because 5.8 is sufficient to give this 1.7 and give this one 5.1. So both of them will be on. And for all values between 5.8 up to 10, the output voltage will be fixed at 5.8. So where does the rest of the voltage go? Or where the rest of the voltage drop go? Well, it will go as a drop across this resistance R. So a current will flow, and there will be a drop across this resistance, and it will have this polarity here, plus and minus. Okay? The same thing happens when you go to the negative cycle, negative part of the cycle. So if you have minus 1 volts, minus 1 meaning you are making this terminal more positive than this one, but this voltage is not sufficient to turn this one on, to give this 1.7 between here and here, or give this one 3.3 between here and here. Okay? Remember, if this one is on, then the anode must be higher than the cathode by 0.7. And for this one to be in the breakdown, the cathode must be higher than the anode by 3.3. So at least you need a voltage of 4 volts between here and here. So this point must be higher than this one by at least 4 volts. So the input will start to go down, minus 1, minus 2, minus 3. At minus 4, this when the two zeners will turn on. One of them is this one, will be in the forward region, okay? This one is the forward region, okay? So current will flow actually this way, okay? So one of them is in the forward region, the other one in the breakdown region, okay? And these two currents will be equal, of course, because they are passing through the same devices. And in that case, the output will remain fixed at minus 4 volts. Remember, V output is this side relative to this side, while this is 0.7 and this is 3.1. So between here and here it's 4. So between here and here it's minus 4. Okay? So the output will be trimmed at two values, 5.8 in the positive direction, minus 4 in the negative direction. Where does the rest of the voltage go in the negative cycle? Well, there is a current flowing in this direction, okay? and this current causes a drop of plus and minus across this resistance here, and the resistance will absorb the rest of the voltage drop. So the current will be adjusted. This current here will be adjusted at every time in order to make this resistance absorb the rest of the drop. So this is a typical example that you determine the region of operation and the circuit will determine the current for you. Actually, we can determine the current for any input voltage value, because you simply in the forward direction, so say Vn, if this branch is on, it's on in this direction here, this direction, so in the positive direction. So you say the current is equal to Vn at any time minus 5.8 divided by 1K. So as the input is increasing, the current will also increase. In the opposite direction, the current is equal to Vn, which is going to be a negative value, okay? Vn, so this side is more positive than this one, minus 4 between here and here. This is forward bias, this is breakdown region, divided by 1K. So you can determine the current actually how, and the current will be, of course, will have when they conduct it will have a sine waveform. It would be a part of a sine waveform. Okay, so this is what I mentioned in the previous slide. There are two ways that this will conduct. First, this Zener diode acts as a diode, and then it will give you a drop of 0.7 between here and here. And this one here will act, the other one will act as a Zener, and then it will require a voltage of 5.1 to break down, okay, between the cathode and the anode. Okay, so the applied voltage between here and here must be at least 5.8. The other way for these two to conduct is for this Zener diode to be in the forward direction. Remember, it's a diode, so it can be in the forward direction, and this one to be in the breakdown. So if this one in the forward direction, then you have between here and here a voltage drop of 0.7, and for the other one to conduct, you have between here and here, between the cathode and the anode, you have 3.3 volts. Okay, so now this is what we know. In the positive part of the cycle, the output will follow the input until the input reaches 5.1 plus 0.7, so 5.8. In that case, the output will be trimmed at 5.8, and the rest of the drop will appear across the resistor. The same thing for the negative cycle. The output will follow the input until the input reaches minus 3.3 plus 0.7. Remember, this is negative voltage because this one relative to this one. So when the input drops below minus 4, these two will conduct and the output will stay constant at minus 4. Where does the rest of the drop go? It will go across the resistor. So this is the black line here represent, or black graph represents the input waveform. The black is the input waveform between minus 10 and 10, and the red line is the output waveform. It's trimmed in the positive side by 5.8 and the negative side at 4. Actually, I should be correct. Actually, it's minus 4 volts. Okay, but this means there is a drop of 4 between the first diode and the second diode, of course, in the opposite direction. Okay, so I hope this helps understand the region of operations of different diodes. The easiest way to solve problems with diodes or Zeners: assume a region of operation, try to verify it, see whether it makes sense or not. If it makes sense, if you get a contradiction, then the diode or the Zener will be in a different region of operation. If it works well, your assumption is valid, then your circuit analysis is correct.